In questions 24 and 25 of chapter 12, we're asked to supply the curved arrow formalism that takes the starting material into the product in both cases. The starting material in both problems is a cyclic ester called a lactone. In both cases, we're treating that lactone with a nucleophile. In question 24, this happens to be a Grignard reagent called phenyl magnesium bromide. Question 25, it's a reducing agent called lithium aluminum hydride. So we're asked to show how the arrows flow in making the new bonds to end up with the respective products. So let's go ahead and put some numbers in just so we can follow how the bonds are being made in these processes. So let's label the carbonyl carbon as number 1. This carbon is going to be 2, 3, 4, 5, and the oxygen will be 6. Let's do the same for the product. I'm going to arbitrarily start here as 1, 2, 3, 4, 5, and 6. This numbering in the product will become apparent as we draw out the mechanism. So in considering a Grignard reagent, the carbon bonded to the metal is going to be partial negative, and the metal itself will be partial positive. So keep in mind that this is opposite of bond polarity, which we have seen in Organic Chemistry 1. Doing the same thing for the major functional group in the starting material, this oxygen is going to be delta minus. The associated carbon is delta plus. So we want to match these partial positive charges. This carbon, which is delta minus, wants to form a bond to this carbon, which is delta plus. The electrons in this bond will then attack that carbon. So this is showing us the new bond that's going to be made between this carbon and this carbon. We know that a carbon atom can only have 4 bonds. At this point, we're going to break the CO pi bond. The electrons in that bond are going to go on oxygen. The oxygen is now going to bear a formal negative charge. The counter ion for that is the magnesium bromide. The magnesium will bear the formal positive charge. We'll put in our other ring oxygen, and then finally, I'm going to abbreviate the phenyl group as pH. So if we look at the product we're trying to form, this carbon has 2 phenyl groups, so we have to add another phenyl group to that carbon. What happens now is this intermediate will break down and the ring oxygen carbon bond will break. So you'll notice in this step, this is how we open that ring up to get the acyclic structure. So this is carbon 1, then we have 2, 3, 4, 5, and the oxygen 6. 2, 3, 4, 5. And then our O, MgBr. Now at this stage, we need to convert this into the product. So we're going to add a second equivalent of the Grignard reagent. We're forming a carbon-carbon bond. We have to break a carbon-oxygen bond. That's going to get us to the magnesiated alkoxide, which is then protonated by the ammonium chloride and water, ending up with our final product. In question 25, we're essentially doing the same thing, except the nucleophile now is hydride, supplied by the lithium aluminum hydride. So if we think of that reagent having the following Lewis dot structure, lithium is going to have a formal negative charge, or excuse me, aluminum is going to have a formal negative charge with a positive lithium counterion. Aluminum does not like to be negative, so it is going to donate this hydrogen as hydride. The electrons in this bond will attack that carbonyl carbon, much the same way as the Grignard attacked the carbonyl in question 24. And our byproduct is AlH3, alane. This intermediate is now going to break down in a similar fashion. We're going to reform the carbon-oxygen pi bond. We're going to break the carbon-oxygen ring bond. So this can be considered a leaving group. So notice in question 24, this intermediate product is a ketone. Now that we've added hydride, the intermediate product is an aldehyde. So the remaining step is the introduction of a second hydride equivalent. So we have to add that second hydrogen. We can show the alane complexing to the carbonyl oxygen and then delivering a hydride. That introduces the second hydrogen bonded to that alcohol. So whereas in 24 we ended up with a tertiary alcohol, in 25 we're ending up with a primary alcohol. So the take-home message for this problem, when you have an ester in the cyclic form as a lactone, the ring will open up and you can add two equivalents of whatever nucleophile is shown in the reaction. The second step is typically an aqueous acidic workup. So we've shown the production of a tertiary alcohol and a primary alcohol.